Hey folks, this is John Buck. I'm back with another discrete time linear systems video, and this one is picking up from the one on discrete time processing of continuous time signals. I'm going to show an example of finding the Fourier transform in discrete time when we start in continuous time with sampling. And so if you haven't watched that video, you should pause this one, go back and watch that one, and then come forward to this one. Again, one of the things we saw in that video, we finished with the 3 steps that say if we want to find a discrete time Fourier transform from the continuous time one when I'm sampling, I'm going to make copies every 2 pi over t, scale the height by 1 over t, and then multiply the last step, multiply the frequency axis by t to get the discrete time frequency. So let's see how that works out. Imagine my signal was Fourier transform looks like this, and my t is 1 over 300. So one of the first things I want to figure out is say, well, what's my continuous time sampling frequency is 2 pi over t, so that's 2 pi over 1 over 300. So that's 2 pi times 300. Again, we usually don't multiply the 2 pi through because if I leave it this way, this is the number in hertz inside the round brackets. So if I do that, the first step is saying making copies of this every 2 pi over t. So I'm going to bring this over and spread it out some. Let me put the 0 here. Right, so this copy is centered at 0. And then the next copy would be, if this is 100, 200, 300. And I'm going to make the copies in color just so we can see. So this is the one centered at 300. So this frequency here is 2 pi times 300, which is omega s. And then on the other side, I'll have one, again, if this is 100, 200, 300. So I'm centered here. And I've got the same width. Right, so these are my copies. This is step 1. Copies every 2 pi over t. And there would be more too. There'd be another one out here. I have another one out here at 600. And so on. They go on, right? Every 300 in frequency the whole way, and another one off to the left here if I was going to be more complete. Right, so when I do that, that's step 1. The next step is to scale all the heights by 1 over t. So all these, instead of being height 1, they get multiplied by 1 over t. So they're all 300 tall. So this is steps 1 and 2. And then the last step, step 3, is I need to multiply the continuous time frequency axis, this omega, by t to get the discrete time frequency. So when I do that, let me move down. I get the same basic picture, but now, this is my 0 point, I have to relabel all these frequencies, right? So this edge right here is now 2 pi times 100 times t, right, which is 2 pi times 100 times 1 over 300. So now to get the discrete time frequency, this is telling me that at that right edge, this is now, let's see, that's pi times 200 over 300, so this is 2 pi over 3. Right, and then this next copy here, well, this was at 2 pi t, or 2 pi over t, so when I multiply this by 1 over 300, the 300s cancel out, and this copy is at 2 pi. This edge here would be minus 2 pi over 3. This would be minus 2 pi, and again, these all, oh, that one should be the green one. But we see that by multiplying by t, we're guaranteed to meet one of the rules, right? Every discrete time Fourier transform has to repeat every 2 pi, and so the sampling has made this repeat every 2 pi. This next copy up here will now be at 4 pi, Another one over here at minus 4 pi. And so on. And again, they're all still with height 300. So this will be what my spectrum looks like. Just this one here for completeness would be 2 pi minus 2 pi over 3, which would be 4 pi over 3. Same thing here. This one would be minus 4 pi over 3 plus 4 pi over 3 here. So this would be, I should label all my axes. This is my discrete time Fourier transform after sampling. Okay, so that's all for this example. We're going to keep doing this in parallel. Talk next about the different steps in the filtering process and then the reconstruction to get the overall system put together. I'll see you in the next video.